Today we're going to talk about an introduction to analytic combinatorics. It might seem a bit strange in a course entitled Analytic Combinatorics to not get to this topic until the middle of the course. But as you'll see, it builds upon all the things that we've talked about to this point and gives us a coherent starting point from where we can go forward in the analysis of algorithms and the analysis of combinatorial structures. And I hope by the end of this lecture you'll have a pretty good idea of what analytic combinatorics actually is. We'll just start with a brief overview. The analytic combinatorics is a calculus for the quantitative study of large combinatorial structures. And most of the work behind analytic combinatorics is set forth in our book Analytic Combinatorics that'll be the basis for part 2 of this course. But it also plays an important role in the analysis of algorithms and in the tie between elementary combinatorics and the kind of analysis that we need to really study computer programs. So the basic features of analytic combinatorics is that we begin with formal combinatorial constructions. So that is, we have a mathematical way to specify what it is that we're studying. The generating function that we've talked about in the third lecture is really the central object of study in analytic combinatorics. Number one, because we have transfer theorems that can immediately give us generating function equations from the combinatorial constructions. And number two, because we can take transfer theorems to give us estimates of the values of things right from the generating function. As I mentioned last time, our asymptotic results are going to extend in principle to any desired precision on the standard scale. And most important is that it's a calculus, that is, we can handle variations on fundamental constructions very easily, and those kinds of variations help us cover a very broad variety of problems for study. So this is just a graphic depiction. We start with combinatorial constructions, and we use a symbolic transfer theorem to get a generating function equation. And that process is sometimes known as the symbolic method. Then from the generating function equation, we use analysis, and we use the analytic transfer theorem to get our coefficient asymptotics directly. Essentially, this process allows us to avoid a lot of the detailed calculations that we've been doing in the analysis of algorithms and combinatorial structures. For example, in analytic combinatorics, if you want to know the number of binary trees with n nodes, there's a combinatorial construction, and we'll go through the details of this, that immediately transfers to a generating function equation that immediately transfers to coefficient asymptotics for the result without going into all of the detail. That's the overview. We'll end the lecture with this slide too, and you'll understand everything that goes behind.